Hi, everyone. Welcome to week 4. I'm Professor Rios. Hope you're doing well. This week, we move into the realm of more application of atmospheric information. So, air pressure, wind, circulation patterns, that kind of stuff, circulation of the world ocean. This ties back to weeks 2 and 3. So, you'll hear some information that was already stated. And this ties into next week as well, or the next set of units. So again, it all kind of ties back together. Having said all that, let's get going. So, when you look at this image here, you can see the white caps on the ocean. You can tell it's a particularly windy day, and there's a reason for that wind and how that wind originates. These are the lesson objectives. So, a total of 8. We get into local, regional, and more global kind of wind patterns. So, we break it down from the atmospheric global circulation down to local winds, which you might experience, say, at the beach or on the mountain or in a valley and so on. So we'll talk about those. First, we'll address the idea of pressure, atmospheric pressure, and we mentioned maybe last class or 2 classes ago, that the atmosphere, whether it's pressure or density, it changes very quickly with height. Both density and pressure do so. So you don't have to go very far up in the atmosphere, say 2,000 meters, and your pressure is significantly lower. All right. So again, the idea of atmospheric pressure and density at the near the surface, everything is sort of piled together much more closer. Whereas if you go higher up, say at the top of a mountain, pressure and density are lower. I think I've used the example of buying a bag of chips or a water bottle at the beach, so sea level, and suddenly you travel to a mountain that's 10,000 feet in elevation, and that bag of chips is poofed up like a big old pillow, and that's because there is lower pressure acting on it, so the air can expand, and that's what you're seeing there. Again, as altitude increases, both pressure and density decrease very rapidly. This is nothing more than a review of material we've addressed before. The nature of wind, you have to think of wind as a recipe, and that recipe is pressure gradient force, Coriolis, which we'll get into, and friction. Pressure gradient force, as we will talk about, is simply the difference in pressure in the horizontal. So, for example, what's the difference in pressure between New York City and Albany? If that pressure is very, very weak, meaning pressure at both is roughly the same or very close, then winds tend to be very light. However, if the pressure is very, very strong between Albany and New York, the corresponding wind will be strong as well. Okay, so it's a very simple relationship between pressure gradient and wind. And again, that is created initially by a differential in temperature through unequal heating. Winds will move from high to low pressure. So here's an example. If pressure gradient were the only force acting on wind, you would simply have air descending and heading towards low pressure where it would rise. Obviously, that's not the way it happened in the real world. We have to worry about 2 other forces, and that would be, and by the way, here's a weather map. So this weather map here shows you that there's a big pressure gradient right through this state, which is Nebraska. And as a result, the winds are very strong. You see that little wind barb with 4 lines through it means 44 to 49 miles an hour. Now, if you look down here in Texas, notice that there's only 2 lines going through. So the weak pressure gradient here implies a wind of only 9 to 14 miles an hour. So again, strong pressure gradient, strong winds, weak pressure gradient, weak winds. That's a very reliable association to make. Coriolis is what happens. It's sort of like an implied force, meaning you have the Earth. The Earth is a sphere. It is rotating, but the atmosphere on top of that, which is this thin layer, is also rotating. So freely moving objects in the northern hemisphere are usually deflected to the right. Freely moving objects in the southern hemisphere are deflected to the left. And this is the reason storms spin the way they do. This is why a hurricane looks the way it does in the northern hemisphere. Again, it's what gives weather systems like winter storms or hurricanes that very distinctive curl to it. There's a couple of examples in the book that show you sort of like a merry-go-round example. And in the YouTube page, there is several animations that I think do a really, really good job. So I really want you to go here. They're like 3 to 4 minutes long, and they do a very good job explaining Coriolis, like why do storms spin the way they do. The other force acting on wind would be Coriolis. So if we're talking about a relationship or a sum game between high pressure and low pressure. Low pressure, the pressure gradient force is directed toward it, and Coriolis is directed towards the higher pressure, because in the northern hemisphere it's acting to the right. So this arrow is to the right of the wind. Okay, and so as a result, the wind is literally along the pressure lines. And this is frankly what happens in the real world, very high up, away from buildings, away from mountains, away from the ocean surface, say 5,000-10,000 feet above the ground, where there are no obstructions to windfall. In reality, we do have friction. So notice, this upper level example would be this right here, wind blowing unimpeded. The closer you get to the ground, where you have trees and forests and buildings and mountains and that kind of thing, is where friction, and this is called the friction layer, this is where friction begins to make winds do strange things. Think about what happens when you go to New York City during a windy day. You may be walking, say, along an avenue, and the winds are not particularly strong, and suddenly you get to the intersection of an avenue and a street, and suddenly the wind just smacks you in the face because of where they happen to be blowing from. They get funneled and channeled, and as a result, that's friction. That's the effect of friction. Cities tend to, you think about the idea of the windy city, right? Chicago. It's not necessarily because it's windier than any other place. It's because the buildings create that effect, so to speak. So the bottom line here is surface winds are a combination of these three forces: the pressure gradient force, the Coriolis, and this recipe will yield winds that blow across pressure lines, winds that converge in low pressure and diverge away from high pressure. And this will be the example that you will see in your book. In the northern hemisphere, winds are spiraling in at the surface, whereas during high pressure, the winds are spiraling out. Okay? Or if you want to think of it three-dimensionally, the air is spiraling in towards the center, and then they collide and rise. And when that rise happens, you get clouds and weather, that kind of thing. Conversely, when you think about the idea of high pressure, the air is sinking, hitting the ground, and spreading away. And that's what you see here, air sinking and spiraling away from that center. And that's called an anti or opposite of cyclone, anticyclone. Usually high pressure is associated with good weather, clear weather. Usually low pressure is associated with cloudy weather, stormy weather, rainy, snow. Think about a hurricane, think about a winter nor'easter, right? That's a cyclone. When you have beautiful high pressure and it's clear and it's sunny and the winds aren't blowing particularly hard, you tend to think of high pressure or an anticyclone. So now you can look at winds in a more localized manner. So the sea breeze is the one that you probably experience the most. Sea breeze and land breeze. So what happens is the land heats up very quickly. It does so more quickly than the ocean. It has a low specific heat. And the water heats up more slowly. So during the day, the winds blow from the ocean onto the land. They rise and they sink, and they create this little convection cell. At night, because the land cools quickly, now everything reverses, and now it's called a land breeze, where the winds are basically blowing out to sea. And so you literally reverse this little loop. And if you've ever been to the beach and you felt the wind coming in strongly out of the ocean, you're experiencing a sea breeze. And you can go 5, 10, 20 miles inland, and the winds can be completely opposite because it doesn't always travel very far in. So this is the idea of a land and a sea breeze. It's a circulation that is driven by heat differentials, the difference between the land and the ocean. The same thing happens, frankly, inland in what's called the mountain valley breeze setup. So the one place in the United States where I have experienced this very, very strongly is at the Grand Canyon. Because the Grand Canyon is a big, giant canyon, as the name implies, and you're basically during the day heating the center of it, and that air is rising really, really fast. And if you're near the edge of the canyon during the day, you can experience winds 20, 30, 50 miles per hour rushing up the side of the canyon. At night, you have a very dangerous opposite, where now the air is cooling, so it's going to sink because cold air is heavy. And now that air is rushing down the mountain, called a valley breeze. And you literally reverse. Notice how it's up, down. Here it's down, up. And you have to be careful if you're near a cliff or an edge, because you could be literally shoved over by the wind. It's no joke that strong. And if you ever go to the Grand Canyon, you will see signs along the walkways that tell you that. They look really weird, but they're basically telling you don't get too close to the edge because the winds are strong enough to possibly push you over. It's a weird sign to see, but you do see them when you visit the Grand Canyon. So here's an example of a very basic weather map. This is low pressure over the state of Illinois, high pressure over Alberta, Canada. Notice how air is spiraling away from the center and spiraling in. Notice that wind, that wind, that wind, that wind. It's all spiraling in towards this center of low pressure. And this is the combination of pressure gradient, Coriolis, and friction. The global atmospheric circulation. So this is a model. Remember, we talked about models during the very first lesson. Models are ways of representing something complicated and stripping away a lot of the stuff you don't care about necessarily at the moment, and then looking at it a little bit more simply. So if you do that with the Earth, which is this super complicated system, you can now break up the Earth into regions. So 60 degrees to 90, 30 to 60, 0 to 30. And there you find areas of general wind in a certain direction. These are the polar easterlies. These are the westerlies in the northern hemisphere, and the northeasterly trades. Where the air diverges, you have high pressure. Where the air converges, you have low pressure. Where the air converges, you have low pressure further north. Okay, and these are regions that basically set up. This is what's called the global atmospheric circulation model. It's a simplified look at the Earth and its wind systems. So you tend to have high pressure, low pressure, high pressure, low pressure, and then you repeat that in the southern hemisphere. So here is basically this image here is basically from here to here, but looked at in the vertical. So here you have the equator where the air is heated most intensely, the air rises, the wind converges, the trade winds, right? Converging air, low pressure, cyclone. This is called the Intertropical Convergence Zone, ITZZ. It is also referred to as the equatorial low, and it's generally an area that's very cloudy, very wet, very rainy, stormy. That air rises and spreads apart, and then it sinks around 30 degrees south and 30 degrees north. That is high pressure, or STH, subtropical high. High pressure, good weather, clear skies. This is where you find the majority of deserts on Earth. ITZC, low pressure, wet weather. This is where you find the majority of tropical rainforests on Earth. Okay, so let's look at that from the perspective of an image. So here's an image. So let's go back to this. Low pressure, high pressure on either side. Clear weather, cloudy weather, clear weather. In this image, here it is. Here's the ITZZ, cloudy. Look at that almost straight line. On the other side, you have high pressure here and high pressure here. So high, low, high. High, low, high. So it becomes pretty predictable. And again, it's a model. So it's taking something complicated, which the atmosphere is, and putting it in an image and in a way of looking at it that makes it simpler to look at. Okay, so the ITZZ, or equatorial low, again, that would be this, there's intense heating, there is lifting, rising air, low pressure, you're releasing latent heat, and there's a lot of clouds and precipitation, generally speaking. Now, looking at where you tend to find it in January versus July, it moves with the seasons. It isn't a perfectly straight line, but it's pretty straight, relatively speaking. But I just want you to get the sense that it moves north and south with the seasons. Now, on the other hand, subtropical high, usually that would be roughly here, like the Sahara Desert, quiet, the air is sinking, there's high pressure, skies are generally clear, and there's very little precipitation. So that's how you sort of model all this in a way that makes it easier to follow. All right, so wind patterns. So there's basically 6 total winds. You have the trade winds, north and south. These are the winds that are basically found between the tropics of Cancer and Capricorn, and they tend to converge roughly at the equator. And these are the winds that move tropical weather systems from east to west. In our latitude area, so we're in the westerlies, the middle latitudes, and we'll talk about more of these next lesson. These are basically moving weather systems from west to east. See the difference? East, west, west, east. And then at the very, very top and bottom of the world, if you want to view it that way, or at the extreme north and extreme south, you have the polar easterlies, which are basically high pressure cells, roughly centered near the north and south poles, generally speaking. So these are the wind systems. So there are 6 wind systems, and there is a total of 7 pressure systems. Okay. So generally speaking, this is what it would look like in January. So our winter versus July, our summer. Notice how this shifts from here to here during January. So everything shifts north and south following the sun, okay, where the sun is shining most directly over. And here's an example. This is a Mercator projection of satellite imagery. Notice the ITCC, so there's this sort of general area of cloudiness that you can generally find near the equator, all the way across. On the other side, you have subtropical high over the Sahara, subtropical high south of that. These down here are mid-latitude weather systems. Notice they look like big curls, like hooks in a way. That's because of Coriolis. And then on the opposite end, you have the polar caps and high pressure. So notice low, high on either side, low on either side of that, high on either side of that. So there's a symmetry to it. Again, it's a model, so we've taken something super complicated, which the atmosphere is, and we've turned it into this somewhat easier to manage conceptual model, okay? A real example or animation of the GAC is available on the YouTube page. There are several animations that I think are worth your time. You should watch them. They're like 3 to 4 minutes long. That's it. We're not talking long videos or anything like that. But I make the reference to the YouTube page, and rather than show it to you here, it'd be good for you to go to the actual YouTube page and get the info there, because there might be other things that you want to see anyway. And again, they're not particularly long in terms of how long each of them takes. Now, regional scale winds, the most common type would be a monsoon. And a monsoon is a very misunderstood wind. A monsoon does not mean wet. Never does, never has, never will. So get that image off your head. A monsoon is nothing more than a seasonal reversal of wind. It is not defined by precipitation. It can be, but there are places where the monsoon is super dry. Not a drop of rain falls. It is a disturbance in the global circulation of the atmosphere. So it is a disturbance to that idealized model that I just showed you. And you tend to find them in places like Africa, Iraq, Saudi Arabia, Vietnam, and of course the most obvious and famous one is the Indian monsoon. But everybody thinks of the Indian monsoon as all this heavy rain. Well, guess what? That's during the summer. During the winter, it's a monsoon as well. It's just dry. The winter coming down the Himalayas. So this is India during the summer. Notice the winter coming out of the Indian Ocean. Yet during the winter coming down the Himalayas. So this is dry, this is wet. China, Vietnam, the Philippines. Wet, dry. Australia, dry, wet. Air coming out of the equator, basically, very wet. Air coming out of the middle of Australia, very dry. Africa, air coming out of the Sahara, very dry. Air coming out of the equator of the Atlantic Ocean, a very warm ocean, very wet. Air-sea interaction, so how the atmosphere and the ocean influence each other. So there's always a heat transfer. That transfer is responsible for the creation of, surface currents. Think about the Gulf Stream off the coast of the United States. There's a cold current on the other side of the country called, that's a cold current coming down from Alaska. So that's very cold, so it has a different set of conditions associated with it. Again, here's an example from the textbook where you tend to find warm currents and cold currents. Warm currents are in the red, of course. Blue currents imply cold. And here's an example, for example, what the Gulf Stream looks like. It's like a ribbon of warm water coming out of the Gulf. Get it? It's called the Gulf Stream. And it goes in between Cuba and Florida, and then it travels north and east, basically bathing Europe in relatively warm water, comparatively speaking. Okay. We'll get into the idea of the thermohaline circulation. So this is now not just a surface current, but a three-dimensional current. And there is a surface component where you see it in white, and then there is an underwater current that you don't see, which continually circulates water across the Earth. This is called the thermohaline circulation because it is a combination of temperature, thermo, and haline implies salt. And the heaviest possible water is water that is both cold and salty. The lightest water is water that is very warm and fresh. So where you tend to have this sort of combination, you have water eventually sinking, creating this conveyor belt of water that regulates temperature across the Earth. If this system were to be stopped for some reason, the climate around the world would change dramatically because all the excess heat would remain down here and the northern and southern regions would become really, really, really cold. Because in a way, ocean currents and air currents are basically taking excess heat from the equator and transporting it to the north and to the south. El Nino, Southern Oscillation, also referred to as ENSO. It is an intermittent anomaly, meaning something different from the norm. That's what that word means. Anomaly, different or very outside the norm in sea surface temperatures. So it is a recurring disruption in the ocean that affects weather and climate across the world. So the El Nino part is the one that you may be familiar with. It is the warming of the equatorial Pacific coast off South America. So Ecuador, Peru, and the Southern Oscillation is simply the difference in pressure between Darwin, Australia, and the island of Tahiti. And you might wonder, well, that seems random. Why those two? Well, the pressure in those places is usually pretty reliable, meaning it's reliably the same depending on when you record it. So if that pressure begins to change, then it's telling you something is happening. So it's like a little warning system, essentially. So this is El Nino. During an El Nino year, the Pacific Ocean out here is very warm compared to what it normally should be. And so this area, which would be high pressure, becomes low pressure. This area, which is low pressure, becomes high pressure. This is usually dry. It becomes very wet. This is very, very wet. Normally, it goes dry. So you're literally flipping the norms around. During La Nina, it is even stronger high pressure here than it usually is, and even stronger low pressure here than it usually is. So this is like normal plus, if you want to think of it that way. Okay. El Nino is measured by these temperature differences from the norm, either warm differences or cold differences. So El Nino is in the red, La Nina is in the blue. And notice that there's no real pattern. They tend to happen every 3 to 7 years. There's no, okay, it's time for El Nino. There's no, you can't say that. There's no real obvious, this is what happens when this happens. But they're somewhat predictable and you can kind of see them coming. So during El Nino event, you tend to have these kind of conditions compared to normal year. Okay. And that's the lesson. Next lesson, we'll talk about atmospheric moisture and wet water balance, precipitation, air masses, fronts, and other disturbances of the atmosphere. Again, as always, there is a live study hour. Make sure you go to Blackboard for that link. If that time again does not work for you, let me know and I can set one up for you. If you have any questions, send them by email as well if you prefer that. We can address any concerns you have that way. Again, don't forget, go into the weekly folder and look at the to-do list. Make sure that you know what to do this week. And of course, there is a Google Earth component to the homework. So make sure that if you have any questions with the Google Earth, that you ask. Otherwise, have a great week, and I hope you're doing well, and we'll talk to you soon. Bye.